Well, last time we have defined uh, the length of a parameterized curve. So here we prove that uh, if beta is reparameterization of alpha, then they have the same length. So, well, let us write the statement. So, this is page 1. So, so topic reparameterization. So topics. Reparameterizations and curve length, and second is unit speed reparameterization of regular curves. Okay, let us state the theorem 1. It says that if beta is a reparameterization of alpha, then length of beta equal to length of alpha. So this is a statement. So we prove this theorem. Proof. So basically proof is very simple. So first, so beta is reparameterization of alpha, means beta equal to alpha composed with h. So well, let us write explicitly alpha is from a comma b to Rn, and beta is from C comma D to Rn, and H is function, so bijective differentiable function from C comma D to A comma B, bijective and differentiable function. So if derivative of, so first we consider the case when the case 1 h prime of t greater than 0 for all t belongs to C comma D, that is beta is positive parameterization of reparameterization of alpha, and case 2, so in case 2 we consider beta is negative reparameterization of alpha, that is h prime of t less than 0 for all t belongs to C comma D, that is so uh, so recall that beta is reparameterization of alpha if it is either positive or negative reparameterization of alpha. Okay, so we have two cases to be considered. So page 2. So first we consider case 1. So well, we have beta u equal to alpha composed with h of u. Then by chain rule we have beta prime of u equal to h prime of u times alpha prime of h u. So derivative of alpha at h u. Okay, so and so this is real, and this is a vector in Rn. So this implies norm of beta prime of u equal to mod h prime of u times norm of alpha prime of h of u, and this is h prime u, this is greater than 0, so mod of h prime u, that is equal to h prime of u times uh, times alpha prime of hu. Now we use change of variable formula for integrals. So using change of variables formula for integrals, we have what alpha prime of t norm of this dt over a to b. Okay, this is equal to the length of alpha, and this is equal to uh, norm of, so we are replacing, so we are replacing t equal to h u. Okay, so we are replacing t equal to h u, then when t equal to a, so h of so h of c equal to a and b equal to h of d. Okay, so because h is bijective differentiable function from c to c comma d to a comma b, so h is bijective differentiable function with positive derivative. This implies uh, so limit so so limit u tends to c h of u equal to a, and limit h tends to, so increasing to uh, d h of u equal to b. So using change of variable formula for integrals, we have this is equal to alpha prime of h of u norm of this times h prime of u du, and limit is from c to d, and from here we have this is equal to integration c to d norm of beta prime of u du, and this is equal to length of beta. Okay, so for the case when beta is positive reparameterization of alpha, then we have length of alpha equal to length of beta. So case 1 is done. Now we consider case 2. This is page 3. So here h is bijective differentiable function from c to c comma d to a comma b, h prime of t less than 0 for all t in the interval c comma d. Then we have, in this case we have limit uh, limit u or limit t decreasing to c h of t, this is equal to b and limit t increasing to d h of t, this is equal to a. And again we use change of variables formulas. So we have, and here also, so beta prime of u. So by chain rule we have the similar, so this is equal to uh, norm of h prime of u times alpha prime of h of u, and this is equal to mod h prime of u times norm of alpha prime of h of u. And here, so in this case h prime of u, that is negative. So this is mod of h prime of u equal to minus h prime of u times norm of alpha prime of h of u norm. So again we use, again using change of variable formula for integral, we have length of alpha, this is equal to integration a to b norm of alpha prime of t dt, this is equal to integration d to c alpha norm of alpha prime of h of u h prime of u du, and this is equal to integration d to c minus h. So this is equal to, from this, so from this equation, minus h prime of u times alpha prime of hu norm alpha prime of hu, this is equal to beta prime of u. So this is equal to d to c minus norm of beta prime of u norm of beta prime of u du, and this is equal to integration from c to d norm of beta prime of u du equal to length of beta. Okay, so this is the proof. Okay, so now we go to the next topic, unit speed reparameterization. So if you are given a regular curve, then you can reparameterize as unit speed curve. So the theorem, this is theorem 2, let alpha from a comma b to Rn be a regular curve. Then there exists a unit speed reparameterization beta, unit speed reparameterization beta of alpha. Okay, so that is, there exists some open interval c comma d and some unit speed curve from beta from c comma d, open interval c comma d to Rn. So that is reparameterization of alpha. Okay, so let us prove this theorem. So let us recall the uh, arc length function is for alpha. Is alpha, this is arc length function from, this is with domain a comma b to Rn. So consider, so this is arc length function which is defined by S alpha of t, this is equal to integration, so limit is, upper limit is t and some base point c, and integral is norm of alpha prime of u du, where c is some fixed base point which is in the domain open interval a comma b. So consider this defined by this. So this uh, S alpha is arc length function of alpha with base point c. Then so as we have noted that S alpha is always differentiable, and by the fundamental theorem of calculus, d dt of alpha S alpha of t. So what is this? This is equal to alpha prime of t, norm of alpha prime of t, and it is assume that alpha is a regular curve. So this is greater than 0, as alpha prime of t not equal to 0 for all t belongs to open interval a comma b, as alpha is regular. Okay, so S alpha is strictly increasing function and differentiable. So S alpha is strictly increasing, and here we can use inverse function theorem. Inverse function theorem implies if S alpha of a comma b, so this is also open interval c comma d, so if so image of S alpha is open interval c comma d, then there exists h from c comma d to a comma b, the inverse of S alpha, and by so now we consider so now okay, draw a picture a comma b here, and here we have c comma d, and this is the function h, and this is Rn, and this is the function So this is the curve alpha. Now consider beta equal to alpha composed with H. So consider alpha composed with H. This is a curve from C comma D, open interval C comma D to Rn, and this is as beta. Okay, so so as you can see that as this is S alpha is strictly increasing, so H is the inverse is also strictly increasing. So H prime of T, that is so H prime of T, that is greater than 0. So now we claim that beta is the required reparameterization, unit speed reparameterization of alpha. First of all, beta is parameterization of alpha, that is for clear. Now we compute the derivative beta prime of S. This is equal to, by chain rule, this is equal to alpha prime at the point H of S times dH ds, and this implies norm of beta prime of S. This is equal to norm of alpha prime of at H H of S, norm of this times dH ds. And this is equal to so what is norm of alpha prime of Hs? So alpha prime, so here one can see that alpha norm of alpha prime of T equal to derivative of S alpha with respect to T at T. So from here we have this is equal to dH ds at S times dH ds this is dt at Hs, and this is equal to 1 by inverse function theorem. So this is the proof. So we stop here. Thank you.